For a parametric curve where x equals f of t and y equals g of t, the slope of the tangent line is dy by dt divided by dx by dt, provided dx by dt does not equal 0. The arc length of that same parametric curve is built from both derivatives together. It's the integral of the square root of open bracket dx by dt, close bracket, squared, plus open bracket dy by dt, close bracket, squared, dt. Now switch to polar coordinates, where a point is given by r and theta, with x equals r times cosine of theta, and y equals r times sine of theta. Area in polar coordinates has its own formula, built from r squared. It is 1/2 times the integral of r of theta squared d theta. Let's use this to find the area enclosed by one petal of the polar curve, r equals cosine of 2 theta, for theta between -pi/4 and pi/4. First, confirm these are the correct bounds for exactly one petal. At theta equals plus or minus pi/4, r equals 0, so the petal begins and ends there, and at theta equals 0, r reaches its maximum value, so this range traces out one complete petal, no more and no less. Now set up the area formula. The area equals 1/2 times the integral from -pi/4 to pi/4 of cosine of 2 theta, quantity squared, d theta. To integrate cosine squared, apply the half angle identity. This turns the expression into 1/4 times the integral from -pi/4 to pi/4 of the quantity 1 plus cosine of 4 theta d theta. Now integrate term by term. The integral of 1 d theta is theta, and the integral of cosine of 4 theta d theta is 1/4 times sine of 4 theta. So we get 1/4 times the quantity theta plus 1/4 sine of 4 theta, evaluated from -pi/4 to pi/4. Plugging in the bounds, the sine of 4 theta terms vanish at both endpoints, since sine of pi and sine of -pi are both 0. What remains is 1/4 times the quantity pi/4 minus -pi/4, which simplifies to 1/4 times pi/2. So the area of one petal equals pi/8. That's our final answer. Here is the key trick to remember. Before you ever set up a polar area integral, find where r equals 0 first. This tells you the correct theta bounds for exactly one loop or one petal. If you use the wrong bounds, the integral will still compute a number, but silently it will be the area of the wrong region entirely. Now, the most common trip-up. In the parametric slope formula, dx by dt is a derivative with respect to t, not with respect to x. Do not treat dy by dx as something you can compute the ordinary way before eliminating the parameter. Mixing up the parameter t with the original variable x is the single most common sign and setup error here. Here's a teaching tip to avoid that confusion. Whenever a curve is given parametrically, write, quote, everything is in terms of t, unquote, as a reminder at the top of your page. Then compute dx by dt and dy by dt as two completely separate, fully labeled lines before you ever form the ratio between them.